again, just another illustration that is in a diagnostic domain that's akin to something we've talked about. So I'm going to go review a slide that we talked about with the naive Bayesian classifier, and that is we have a joint probability here. I'm on slide 23 now. We consider an ordering of variables that are going to allow us to factor a joint probability. In this case, we've got, want to know the probability of V1 and V2 and not V3 and V4 and not V5. These are all presumably binary valued variables. And you recall that I can factor that in a particular order. Again, the order is, I've given the order up here. I could have picked any order to do this factorization, but I picked one. We assume the following independencies are conditional independencies. Just for the sake of argument, just made these up. There's nothing I've seen so far that would indicate this. But suppose V2 is independent of V1. Knowing the value of V1 has no influence on on the probabilities that apply to values of V2. V3 is conditionally independent of V2 given V1. So if I know the value of V1, that may inform my probability, the probabilities for the values of V3, but if I know V1, V2 adds no additional predictive power. And I can continue with other examples there. By the way, there was problems with Brightspace today. I couldn't download the question as I had asked it on this morning's quiz, but I'll add the key to that as part of these slides as well, because it's relevant to this slide that I just showed you. Now on slide 24, and this is going to be the focus of Thursday's lecture. Bayesian networks, or belief networks as the book calls them, are an important formalism in AI for dealing with uncertainty. And their advantage is that they graphically represent independencies and conditional independencies within a data set. So here's just a brief example that might help you if you want to do some of the reading for belief networks. But I have a particular factorization ordering in mind. Again, I'm on slide 24. And I'm going to construct a belief network that represents or models the data as I briefly introduced it on the previous slide. So I start with a factorization ordering when you're talking about building a Bayesian network. And you take the first variable in that factorization ordering, V1 in this case, and you make it the root of the Bayesian network. And there can be multiple roots in the Bayesian network. That is, multiple nodes or multiple variables that have no parents. And with that root, associated with that root, I store the probabilities of the various values for that variable. So given these are binary valued variables, the probabilities of capital V1 are little v1 and not little v1. And I could represent those explicitly, but I only really need to represent one of them. If I represent explicitly the probability of little v1 as 0.75, I can always compute the probability of not little v1. It's going to be 1 minus 0.75. So I don't need to list every probability. I just need to list all but one probability, and then I can always compute the other, or the final one, as 1 minus the sum of the remaining, or the other variables, values that I've specified. V2 is second in the ordering, and I'm going to be using some of the assumptions I made in that earlier slide, and where I asserted, I just, again, made this up. There's nothing in the earlier slides before that that would have led you to believe that V2 is independent of V1, but simply an assertion that V2 is independent of V1. And if that independence is true, then V2 is also a root of the belief network. And with V2, I would also be storing, in this case, just a single probability, the probability of V2 all by itself. Now, if you go back and you look at the earlier slide, slide 23, where I made that claim, V2 is independent of V1, that gives you a win. It means that you don't have to explicitly store the probability of V2, all possible values of V2 given all possible values of V1, which would be 4 minus 1 probabilities that you'd have to store, because there are 4 ways of 4 patterns of V2 values and V1 values. But you only have to store a couple, or in this case, one of those, because you don't have to store a conditional probability. You can store an unconditioned probability in this case. So now going to slide 25, V3 is a third variable in the third variable in the ordering, and I've stated in the earlier slide that V3 is independent of V2 given V1. So in the graphical representation, I would make V3 a child of V1. It is not a child of V2 because V3 is conditionally independent of V2 given V1. V1 is the only variable I need here to inform the probabilities for V3. And you'll notice here that in this case, I do have to represent conditional probabilities, but fortunately, these conditional probabilities are involve the 2 different values of V3, but they don't involve all possible patterns of V1 and V2 values. It's only V1 values that I have to look at. So I've shown you in dark font that I've got to explicitly represent the probability of V3 given V1, and I've got to explicitly represent the probability of V3 given not V1. But I can compute the remaining 2 probabilities, which I've shown in light font, as 1 minus probabilities that I am explicitly storing. Okay? So again, it saves me having to represent a whole lot of probabilities. It's reducing the number of probabilities I have to store. I didn't say this in the earlier slide, but I'll assert it now that V4 is conditionally independent of V1 given V2 and V3. So I would add V4 here. Its parents would be V3 and V2, which are the ones that are required that condition the probability of the V4 values. And again, this allows me to reduce the number of probabilities. I do have to represent these 4 conditional probabilities that are in dark font, but I can compute the rest as 1 minus each of those probabilities to get the probabilities of not V4 given conditioning information. Finally, let's look at slide 26. I add the last variable. In this case, the assertion is that V5 is conditionally independent of V1, V2, and V4 given V3. That's where this equality at the top comes from. And I add V5 to the network, and its only parent is V3 because of this assertion of conditional independence. So there's two aspects of a belief network that we have to think about representing. One is the topology, what's connected to what, and the other is the actual probability table associated with every node.